focusing on some examples in research articles. During this lecture, I'm going to focus on 2 practice articles. Each practice article has some questions and their answers that are available on the website in Module 4. This will help you start getting some practice at interpreting the research literature. At the end of Module 4, there are 2 quizzes based on 2 different articles that you should take. These are each worth 5 points in your grade. The first article is from Montgomery, published in 2004. In this particular article, these folks measured children, and they measured their physical activity level. So on the y-axis, this vertical axis, PAL stands for physical activity level. They also measured the percentage of time children spent in doing different behaviors. One of those was percentage of time spent being sedentary, and on the graph these are represented by little triangles. They also looked at percentage of time spent performing activities of light intensity. These data are little squares on the graph. And they also looked at the percentage of time that children spent performing moderate to vigorous physical activity, and those are the little X's on the graph. And so this graph has 3 different variables, percentage of time being compared to physical activity level. We have percent time spent sedentary on the far right hand side in the little triangles, percent time spent in light activity in the squares, and percent time spent in moderate to vigorous activity. These are called scatter plots, and there just happens to be 3 scatter plots on one figure because the x-axis is the same. But they also give you some information in the footnote, so it's very important when you're trying to interpret research articles to look at the figure being presented to you and read all of the titles and footnotes and abbreviations, because all of that is going to give you some clues about what is being presented in this article. So let's just focus first of all on the right hand side. The circle is around the data for the percentage of time spent in sedentary activity. So there are a bunch of little triangles on the graph. Each triangle is the data for an individual person. And so each individual has a percentage of time that they spent being sedentary, and they have a physical activity level measured. And by the way, physical activity level was measured using these little devices called accelerometers, and they kind of attach to your waistband, and they can measure and record and save the number of movement counts that occur as you move your body throughout your day. And so they had the physical activity level, and they, with surveys, measured the percentage of time spent sedentary and in these other intensity activities. So the position of each point on this graph is the combination of the value of the y-axis and the value of the x-axis. And then what they did was they ran a correlation on these data. Actually, they did a regression, because there is a regression line through the data showing you the average kind of response here. Also, in the text underneath the figure, they give you some information. I've underlined it. It says the percentage of time spent sedentary is represented by the solid line, and R equals negative 0.33, P less than 0.01. So the R is the correlation. The correlation coefficient is 0.33, and it has a negative sign, and that negative sign doesn't tell you anything about how strong the relationship is, but it tells you the direction. And you can see that the way the line is angled, it's from upper left to lower right. That is an inverse relationship. Compared to the other 2 lines on this graph, those 2 lines are positive, and you'll see that their correlations are positive numbers. So the correlation coefficient was a negative 0.33, and the p-value they're saying is less than 0.01. And we know that p-values less than 0.05 are those that we consider to be statistically significant. So they're giving you some information about the data for this particular variable. And they do that for the others as well. So here is the percentage of time spent in light activity. The R was 0.31. Note it's positive because the line goes from lower left to upper right. And this particular correlation coefficient was also significant because P was less than 0.01. And the final data point here is this last little bit, the X's on the graph. These are time spent in moderate to vigorous physical activity, and there is a line of best fit through those data as well. In the text below the figure, it says the R equals 0.22, and so that is a correlation of 0.22, which is statistically significant because the p-value is also less than 0.01. Now, another thing I want to point out is that these R's that are reported, these are correlation coefficients. We can interpret them on a scale of 0 to 1, ignoring the positive or negative sign. The closer to 1, the stronger the relationship. So of these three, the percent time spent sedentary is actually the strongest relationship. It is that 0.33 is bigger than the 0.31 and bigger than the 0.22. That is the strongest relationship here. Notice I'm just completely ignoring that negative sign with the 0.33. The other thing that you can do with this is you can take those R's and type them on your calculator and square them. You'll get R squared. Multiply it by 100 to get it into a percentage. Then you can start talking about these data as how much variability in physical activity level can the percentage of time spent being sedentary account for. So just take a look at the data for percent time spent sedentary. Look at those values there's some spread in terms of physical activity level. What can account for that variability in physical activity level? There are some people who have high activity levels, some people have low activity levels. Can the percentage of time spent being sedentary account for the varying levels of physical activity? Well, that is answered by taking that correlation and squaring it. So that negative 0.33, you do negative 0.33 times negative 0.33, hit your equals button, and then multiply it by 100 to get it into a percentage. And that will tell you how much variability in PAL can be accounted for by the percentage of time spent being sedentary. Another table in this particular study is shown here on your slide. This is table 2. Now, when I look at tables of data or tables of results, the first thing I do is read the title. The next thing I do is read the headings of the columns of data, and then I also take a look at the footnote, because the footnote can give you clues about what kind of data are being presented. So one thing I want to point out before I go too far is that there are a couple of typos in this particular table. Notice that in the middle of the table the 11.4 is listed twice. That is just a typo. And then at the top it says t squared, and really that's supposed to be r squared. And the reason why I am using this particular table in this class, even though there are typos, is because this is how it was published. And actually we get this all the time. Things get published so quickly that you will find typos in some tables and figures, and so it kind of is just a reality of the speed at which things get published. And so we have to live with the fact that many of these tables will have the potential for a typo or two, but we still have to figure out what's going on in the table anyway. So one thing I want to point out is that the top half of the table is a little bit different than the bottom half, because the variables presented in the top are a little bit different. Well, some of them are different. PAL is listed 3 times on the top half of the table, and in the bottom half of the table it's AEE that's listed, and both of those abbreviations are defined for you. The other thing you'll notice is that regardless of which analysis is being shown in this table, there are a set of 4 variables that are listed below each PAL or each AEE, and they are very similar. It's sex, age, BMI, SD score, and percent sedentary. The next one down, instead of percent sedentary, it's percent light activity. The third one, instead of percent light, it's percent MVPA, moderate to vigorous physical activity. And then the whole thing gets repeated again as you look at those variables underneath the AEE. So there's a pattern here that you're going to pick up on. And so as you're trying to think about what analyses are being presented to me, some clues are being given to you. PAL is listed, and then indented is a list of variables. And the heading of this says outcome and variable. And that tells you something. So really what you're looking at here is you're looking at multiple regression analyses that are being presented. And so if you just read the title of the table, it says multiple regression analyses on PAL and AEE colon effects of, and it lists the 4 variables. And so your job is to try and figure out, well, what is an X and what is a Y? I know these are multiple regression analyses here, and so you should start being able to piece together some information about what is being shown to you. And so if you recall the fact that what makes a multiple regression is the fact that there are multiple X's all being compared to one Y, then this format may start to make some sense. If there are multiple variables in a list indented underneath PAL, probably what we're looking at are those 4 variables are the X's, and the PAL is the outcome, it's the Y. And so in this particular table, there are 6 regressions being shown. The first one is in the red box. And then there's another one, there are 3 in total for PAL, and 3 in total for AEE. Each one of these regressions has 4 variables in it: sex, age, BMI, SD score, and a percentage of time spent in a certain type of activity. So we've already talked about outcome and variable. It's the Y with its list of X's underneath. The next column is called regression coefficient. These are slopes. Notice that each X variable has a regression coefficient. These are betas, they're slopes. So the slope for sex in that very first analysis is negative 0.17181. The next column is P. This is the p-value. P-values less than 0.05 or 0.05 and less are statistically significant. And notice there's a p-value with each X. And so you can look to see which X's are significant predictors of either PAL or AEE. And in the very last column, I've already talked about this a little bit. The T squared is really a typo. It's R squared. This is R squared times 100. It's expressed as a percent. This is the amount of variability accounted for. So if we look at this particular analysis that's in the box, the 4 variables, sex, age, BMI, SD score, and percent sedentary, all together account for 14.8% of the variability in PAL. Okay. Now what's interesting about multiple regressions and looking at the R squareds is that you can start adding and subtracting R squareds. And so another way they could have done this analysis in this particular table is they could have added in each X variable individually. So you could have put sex in first and run the regression and get an R squared. And then you could have added age in, done the regression, gotten the new R squared with both sex and age in. And every time you add a variable, the R squared either changes or doesn't change. If it changes, if it increases, that means you are accounting for more variability by the addition of that variable. Okay, so because R squareds, because you can add and subtract them, this makes multiple regression a very powerful tool. And so in some of the practice questions for this table, I talk about, well, what if I told you that maybe 3 of these variables, sex, age, BMI, SD score, accounted for, I don't know, let's just say 5%. How much would percent sedentary account for? And so if you know that a subset of these 4 variables accounts for a certain percentage, and you also know from the table that all 4 of them together account for 14.8, then you can do some simple subtraction to see what the remaining variables account for. And so there's one or two of those questions in the practice questions you can take a look at. So here is the next multiple regression. When you take out percent sedentary and add in instead percent light activity, the R squared goes from 14.8 to 15. And so the authors are just showing you many of these regressions. Okay, the next article is from Hancock's. This was also published in 2004. And in this study, kind of a unique study, they were looking at television viewing and how youth and childhood television viewing compared to young adult health outcomes. But this is really the first table that they show you in the paper. This is table 1, and you can see the title of the table. It says mean viewing hours and correlation between ages. So they're telling you what's in this table. And so here is the part where it's the mean television viewing hours. And so you can see in the title it says mean parenthesis SD viewing hours. And so that is the mean hours of TV viewing and its standard deviation in parentheses. And so it gives the television viewing for each age listed on the left-hand side, 5 years, 7, 9, 11, etc. It's always important to read the footnotes because some important information is given in the footnotes. And so you can see that there are various stars and little crosses and double hatch marks, and they're telling you something about the data. And so for the ages that have stars next to them, these are weekday averages, and there are 3 ages that have the double plus signs. Those are daily averages, presumably including weekend days. And so the left-hand part of the table gives you mean television viewing hours, and the right-hand part gives you correlations. And this is a very classic way of presenting correlations. This is called a correlation matrix. And notice that the data are kind of half filled out on the diagonal in this kind of presentation. And so there are a lot of correlations that are just not listed there. And so it may be a little confusing to figure out exactly what is being correlated with what. And so I want to help you figure out this correlation matrix. Now there are a lot of correlation matrices that are presented out in the literature, and so this is a very traditional way of presenting correlations, and so you really need to understand how these are interpreted. So here's what you do. If you want to find the correlation coefficient between 2 variables, you need to find one of those variables as a row and the other variable as a column. And so what I've done here is I have highlighted the 11-year-old data and the 21-year-old data. So really, these are correlations of TV viewing between different ages. So this particular blue box on the screen is telling you the correlation between TV watching at 11 years old compared to TV watching at 21 years old. And so what you do is you find the variable 11 on the row, and you find the variable 21 on the column, and you look to see where those intersect. And so the row or the column for those 2 variables intersect at a number of 0.19. You can see that there's a square right around that particular value. That is the correlation between TV viewing at 11 years and TV viewing at 21 years. And so if people were pretty consistent in how much TV they watched as they got older, that correlation would be pretty high. But if, as they got older, their TV habits changed, then that correlation would not be very good. And so this correlation is around 0.19. It is a little bit low. It is still statistically significant because if you look at the footnote, they're saying that all of the correlations were significant except for the one that has a single cross next to it. And there's only one of those in there. So this was statistically significant, but it was relatively low. Also, please note that you could take that correlation, square it, and multiply it by 100 to get the r squared. And that would answer the question, how much variability in TV viewing at 11 years can be accounted for by TV viewing at 21? That would be answered with an r squared. Take that number, r, these are correlations, so these are all r's, and you square it. Okay, so just for a little practice, what would the correlation be between TV viewing at 5 years and TV viewing at 15 years? Notice my question is asking, what is the correlation? So I'm looking for the R, and sure enough, this particular table is giving me correlations. They're giving you the R. You should notice that sometimes tables will give you R squareds, not R's, and so you need to be careful about what kind of number is being presented to you. This is very clear. They label this as correlation coefficients. So what is the correlation between TV viewing at 5 years and TV viewing at 15 years? The answer is 0.16, and here's how I found it. Oops. Sorry about that. So the correlation between TV viewing at 5 years and TV viewing at 15 years is you find the row for 5 in the column for 15, and that is the correlation 0.16, which is sitting right in that area. So the column for 15, the row for 5, that R is 0.16. So that's the answer. We can also ask another question. How much variability does TV viewing at 5 years account for in TV viewing at 21 years? Now notice this is a different kind of question. It's not asking you for the correlation coefficient, it's asking you how much variability is accounted for. And whenever you get a question that is a how much variability is accounted for question, it is always answered with an R squared. If you see that language, how much variability does this one account for in that one, that is always answered with an R squared. And so in this case, we are going to need to find the correlation and then on our calculators square it. And so TV viewing at 5 years and TV viewing at 21 years, we need to find the correlation between those two. So the row 5, the column of 21, there's a correlation of 0.08. That's the correlation. But the question is asking for how much variability is accounted for. And for that, you need an R squared. So let's take the R, 0.08, multiply it by itself, and then multiply it by 100, and you get 0.64%. So really, a very small amount of the variability in TV viewing at 21 years can be accounted for by the TV viewing at 5 years. And so these are not very highly related at all. I just want to point out something, that where the 0.08 is sitting, that's the row for 5 years and the column for 21. But what if you looked at the column for 5 and the row for 21? Well, gee, there's an empty box sitting there. And that's very typical presentation. If they filled in this whole table, you would have correlations repeated twice, because there are two places you can find the correlation between 5 and 21 years. You can either find the row of 5 or the row of 21, and you'll get that correlation. But what they do is, instead of repeating the numbers, they leave half of it blank. And so if you are reading one of these correlation matrices and you find yourself sitting in a spot where there's no number there, it's not that there's no correlation, it's just that you need to look in the other half of the table, and there will be a correlation sitting there. They just don't repeat all of the correlations and completely fill the table. They just list them one time, because that's all that's needed. And I just want to point out that this very small amount of variability accounted for is because this is a very small correlation. It is also not significant because it's saying that this is the only correlation in the footnote where this is not significant. So this is very small, non-significant, and you can see the amount of variability accounted for is really tiny. These two variables are not related. This tells me that as children grew up, their TV habits, their TV viewing habits changed. Now, it could have been that the heavy TV watchers at 5 years became not heavy TV watchers at 21, or the opposite. The light TV watchers at 5 years became the heavy TV watchers at 21. These two are just not related to one another. Now here is the next table in this article. It's a much more complicated table, but I want to try and walk you through this pretty slowly. So first of all, take a look at the title. It's at the bottom of this table. It says Table 2, Regression of Health Outcomes at Age 26 on TV Viewing During Childhood, Adolescence, and Early Adulthood. Okay, so we are looking at how the TV viewing in the younger years is related to health outcomes at 26 years of age. So here is how it's set up. There's a blue box around the first variable that was compared to TV viewing. This is BMI. And then the next variable was something called VO2 max. This is cardiovascular fitness. And so the higher the VO2 max, the higher your aerobic or cardiovascular fitness is. And so they looked at that also. The next one was the blood levels of cholesterol compared to youth TV viewing. The next was whether the young adults were current smokers. And I want to point out that here's another typo. Just take a look at the underline under the headings, and the underline under the headings is a little bit off. What I've circled in my blue box is all of the information that applies to current smoking, but if you look at how the headings are underlined, you might think that there's some of what's in my blue box actually belongs to cholesterol, and that's a typo. And so, like I said, these errors get made all the time, and so sometimes you really have to put on your thinking cap to figure out what's going on. And the last variable was systolic blood pressure. How does systolic blood pressure at age 26 compare to childhood TV viewing? Now I want you to notice for each of these, with the exception of current smoking, but for each of these, the N is reported. N is the number of people in the analysis. The next column is a funny looking B, that stands for beta, and in parentheses is SE, that stands for standard error. It's kind of like the standard deviation of the beta, and the beta is the slope, don't forget. So this is the slope for that variable. And then the last column for each adult health outcome is P. This is the p-value. This is the statistical significance. And so the p-values of 0.05 or smaller are the ones that are statistically significant. Okay, so there are 5 different major adult health outcomes that were compared to childhood TV viewing. And these are all regressions. And actually you'll see they are multiple regressions because there are other variables that are included in these analyses as well. Okay, that leads me to this really big footnote, which is really important to read and kind of sift through. So we're going to try to do that right now. So the first part of this, it says, analyses exclude pregnant women. So anyone who was pregnant at the time that they made these measurements, when these folks were 26 years of age, they were not included in the analyses. They also say that all of the analyses are adjusted for sex, meaning to adjust for sex means they included a variable that designated who were males and who were females. Because when you include that variable in an analysis, it accounts for the influence of gender. Okay, so what they wanted to do is they wanted to look at the role of BMI compared to TV viewing. And to do that, they needed to account for the influence of other variables. And so by adding gender in this equation, they account for its influence. And then you're allowed to look at BMI independently. They go on to say that the analyses for VO2 max are also adjusted for body weight. And so all of the analyses that you see presented for in the VO2 max column, they also had body weight as a variable in that equation. They don't show you the results for that because that's not their focus of this paper, but they're telling you in this footnote that that variable is in there. It's in the equation to account for the influence of differing body weights so that you could look at VO2 max and interpret it correctly. Then they define some terms. They say the funny looking B is called the beta coefficient. BP is blood pressure and BMI is body mass index. And then they tell you something about how they measured and averaged TV viewing, and so they did it differently at some points. There was mean hours per weekday, and then there were mean hours per day, which included the weekends, and so they're trying to tell you that. You can see that those symbols are right in front of the childhood, adolescence, and early adulthood TV viewing on the far left-hand side. Then they also go on to say that there were further adjustments that were made. So the adjusted regression models included childhood socioeconomic status for all outcomes. And so that means for all of these things, BMI, VO2 max, cholesterol, smoking, systolic blood pressure, socioeconomic status was in there. It was in there to account for the influence of socioeconomic status. They didn't show you the results of that, but they're telling you it's accounted for, So now you can look at the effect of each of these variables that are being presented in this table. Then they go on to say, and the following additional covariates. And now a covariate is something which is you want to account for its influence, just like all of these other things we've been talking about. You want to account for its influence because you know it has an impact, but that's not the main focus of your paper. Really, the main focus of this paper is looking at the adult health outcomes compared to the TV viewing. But there are other things that can also affect this relationship that you need to account for. And so those things are listed here. So they say BMI at age 5 and parental BMI for BMI. What that means is for the analyses on BMI that are presented in the table, additional variables included in those analyses was the BMI at age 5 years and parental BMI. And this is to recognize that there are other things that can influence BMI, that can influence that relationship between BMI at 26 years old and TV viewing during childhood. And we're trying to account for the fact that there is a genetic component to BMI. That's why parental BMI is in there. So someone could have a high BMI, not because they watched a lot of TV, but because their parents had a high BMI too, and there's a genetic component. So they're trying to account for that, so they can really look at this relationship between BMI at 26 and the childhood TV viewing. They go on to say, reported physical activity at age 15 years for VO2 max. This means that for the VO2 max analyses, they also included reported physical activity at age 15. So that variable, reported physical activity at age 15, is included in the VO2 max analyses, but is not included in any of the other analyses. There's no reason to put it in the BMI analyses or the cholesterol ones. They're trying to account for fitness levels in those VO2 max analyses. And then they go on to say that, and parental smoking for current smoking, which means that for the current smoking analysis that's being shown in this table, parental smoking was also included as a covariate. Parental smoking is not in any of the other analyses, it's just in the current smoking. Because someone might be more likely to be a current smoker if they're smoking in their families, and that might be independent of how much TV they watched. Okay? So the purpose of this footnote is to describe anything that's pertinent to the analyses being presented, and that's what they're trying to do with this. So what are these analyses being presented here? So let me put a blue box around one single analysis. This is the results of one single analysis. This is the comparison of BMI being compared to mean child and adolescent TV viewing, and this is the adjusted values. Under N, there were 709 people in this analysis. The slope for BMI was 0.48. Its standard error was 0.19. By the way, we're not going to focus much on the standard error in this course, but slope is something that you should be able to look at and make some basic interpretations of. Also, this particular variable, BMI, with its slope of 0.48, had a p-value of 0.0121, which is less than 0.05, which is statistically significant. So this means that BMI was significantly related to childhood TV viewing in these 709 people. What they don't give you in this table at all, they don't give you an R, they don't give you an R squared, so you have no idea how strong this relationship is. You just know it's significant. You can tell the direction of this relationship, though, because you see the slope there. And a slope that is positive means that it is a direct relationship, a positive relationship. A slope that is negative will mean it is inverse, an indirect relationship. And so the slope for BMI of 0.48, it's a positive number. This means that those folks who did a lot of TV watching tended to have a higher BMI. Those folks who did less TV watching tended to have a lower BMI. Now that's not the case for some of the other variables in this particular table, namely the VO2 max data. Remember, VO2 max is fitness. And so in this analysis, there were 657 people measured. The slope for VO2 max was a negative 0.12, and it was also statistically significant. So there was a relationship between fitness and average TV viewing. But this relationship is inverse because that slope is negative. This means that the more TV viewing people did as children, the lower their cardiovascular fitness was as young adults. Or the lower their TV watching as children, the higher their fitness as adults. So it's an inverse relationship. And you can see that by the negative slope. This is another regression for cholesterol, the same idea, N, a beta, and a p-value. Now the data for current smoking are a little bit different. These are odds ratios with a 95% confidence interval. Now because current smoking, this variable is a yes-no kind of variable, it's categorical. Either yes, they're a current smoker, or no, they're not. This means that a different kind of regression had to be run. And this is it's called logistic regression. And so you don't get a beta, you get an odds ratio. But you still have a p-value with this odds ratio. And so there is a significant relationship between current smoking and TV viewing. And so the odds are that if someone did a lot of TV viewing, they had higher odds of being a current smoker. Okay, so that's the only analysis in this table. It's a little bit different. And in this course, we're really not going to get into logistic regression, but you can't just do a regular regression when you have nominal data or categorical data. You have to do a logistic regression. And then the last one is systolic blood pressure, but this is the same as the other variables we were talking about before. So in total, what you're looking at here are 5 different outcome variables: BMI, VO2 max, cholesterol, smoking, and blood pressure. And these are all being compared to TV viewing, and so there are 5 different regressions being presented for each of these health outcomes. So for BMI, there were 2, one unadjusted, one adjusted, and then 3 more for childhood, adolescent, and early adulthood. So in total, there are 25 regressions being shown on this table: 5 for BMI, 5 for VO2 max, etc. Okay, now we're going to get to the 2 articles that you're being quizzed on. So this is Cotter, published in 2010. This is an example of a correlation matrix, and so we saw that earlier on one of the practice articles. Correlation matrix is where the variables are listed down the left-hand side and the same variables are listed across the top. And so the first variable is gender, then race, then health, then age, etc. As you go across the top, 1, 2, 3, 4, 5, 6, 7, 8, 9, those numbers correspond to the variables listed down the left. And so variable number 1 is gender, variable number 2 is race, and so they just didn't have room to write it across the top, so they just numbered them. So for example, if you wanted to look at the correlation between gender and activity, gender is variable number 1, activity is variable number 9, you need to find the row for gender and the column for activity, 1 versus 9. That is a negative 0.1 correlation. The correlation between gender and activity is a negative 0.1. You also notice that the correlations here are starred if they are statistically significant, and they specify 3 different levels of significance: equal to 0.05 or less, equal to 0.01 or less, or equal to 0.001 or less. They also give you a little footnote down here talking about how they coded the variables for gender and for race, etc. So they're just giving you some information about that. So this is a correlation matrix. These are R's, and they're starred if they're significant. You can see some of these R's are positive, some are negative. The positive ones are direct relationships. The negative ones are indirect relationships. Also from Cotter, this is a table of multiple regression analyses. And so what they did is they call this hierarchical. And so another word for this is stepwise. And so earlier I talked about the fact that you can add and subtract regressions. And a lot of times researchers will build their regressions where they have a certain number of variables in the equation, and then they add some more and watch how r squared changes. Then they add some more and watch how r squared changes. And that's exactly what they did here, except they did them in 3 steps. Step 1, step 2, step 3, and that's how it's labeled across the top. The variables that they measured are listed down the left: age, gender, race, education, etc. And so in step 1, you've got 5 variables that are sitting in that equation. Those are age, gender, race, education, and self-rated health. These 5 variables are predicting or being compared to physical activity. So in the title it says hierarchical multiple regression analyses predicting physical activity. The variable that's predicted, that's the y. So physical activity in this case is the y, and the variables listed down the left, those are the x's. So there are 5 of them in the equation. Each has a beta, which is b, and a standard error, which is SE, and then a funny looking b. That is what's known as a standardized beta. And when you standardize a beta, that allows you to compare betas directly to each other, because you eliminate the different units of measure of each of these variables. So age is measured in years, and gender is a coded variable, and race is also a coded variable. Education is a different unit of measure than age, for example. So you can account for the differing units of measure by standardizing your beta. So that's why there are 2 beta columns. One is the raw one, the B, and then the other one, the funny looking B, italicized B, is the standardized beta. When you have a standardized beta, the bigger the number, the more weight that variable carries in the equation. Okay, so under the main column, step 1, you know that there are 5 variables in the equation. Then way at the bottom it starts giving you information about how much variability is accounted for. And so what they do is they give you the delta r squared, that's that little triangle, delta, or change in r squared. So the change in r squared, when you went from no variables in the equation to these 5 variables, was 11.9%. And then what they do is they adjust the r squared based on if the sample size was small. So sometimes you see an adjustment to r squared, and that's done to make the r squared a better predictor of the population. And so you'll see that a lot. So that's why the 11.9, when you adjust it, is 11.8. Okay, it's just an adjustment for sample size. So step 1 variables accounted for 11.9% of the variability in physical activity level. Then they move on to step 2, and in step 2 they added 3 more variables. They added support, strain, and control. All of the other 5 variables are still in there because their betas are also listed as well, and so you have betas for 8 variables there. When they added the next 3 variables, the r squared changed, and that change in r squared is given at the bottom, delta, or the triangle, delta r squared. It changed by 1.6%. When you make the adjustment, it is a total amount of variability of 13.3%. So these 8 variables account for 13.3%. Whereas in step 1, the 5 variables accounted for, when you adjust, 11.8%. And then going to step 3, the last couple of variables were added, and there was another change in r squared, except this one was much smaller. It was 0.3%. And so by doing this in a stepwise way, or hierarchical, you can look at what happens to the r-squared when you add in certain variables at a time. Okay, and so they give you the r-squareds at the bottom. What they also do is they star the betas that are statistically significant, and they give you the levels that the cutoff levels for the p-value at the bottom also. So this is Cotter. This is an example of hierarchical multiple regression analysis, and they give you 3 steps. They give you the r-squared changes at the bottom, and then the total amount of variability accounted for by all the variables sitting in the equation. The second quiz article is by Nordstrand, and in this article, here's figure 1. These are correlations between anthropometric measurements and PWV. And you could take a look at the article to see exactly what these variables are. But really, it's not even important to know what these variables are to be able to interpret the statistics that are being presented. So you can take a look at this table and start making some sense of these analyses. Let me just focus in on a couple of these graphs. So this is just the bottom couple of graphs. These are scatter plots. You have a variable on the y-axis and a variable on the x-axis. On the x is WHTR, and that is predicting the PWV. And so every dot on the graph is a separate person who has one value for x and a value for y. And so I believe these were males and females, and I forget which is on the left and which is on the right, but it tells you way at the top of the page. So these are scatter plots. Within the graph, they show you R equals, and so they give you the correlation right there on the graph, and they tell you if it is statistically significant by giving you the p-value. So these are scatter plots being shown to you, an x compared to a y. The R is given, the statistical significance of that R is also given, and these were done on males and females. Then they went on to do a table of correlations, and instead of a big correlation matrix, they presented their correlations this way, and these are correlations between PWV, body composition, metabolic parameters, and medications. And so when I was first looking at this table, I thought, okay, I see the variables listed down the left, and they're giving a correlation for males and a correlation for females. You know they're correlations because, well, one, they say it in the title, and the other, in parentheses next to male and female, it says R. That's the symbol for correlation. So I know these are correlations. And so for the males, age is being correlated with what? And it took me a minute to figure out what is being correlated with. And I finally figured out that it must be PWV. Look at the title, correlations between PWV, body composition, metabolic parameters, etc. But if you look in the list, PWV is not there. So it must be age compared to PWV, and hypertension compared to PWV, and type 2 diabetes compared to PWV, etc. So each of these in the list is being compared to PWV. So these are done separately for males and females. They give you a footnote at the bottom that you should read. Correlations are starred or identified somehow if they are statistically significant. The star is p less than 0.05. The little cross is p less than 0.001. And then some other things are defined in the bottom. And so these are correlations between each of these variables listed on the left versus PWV, done for males, and then done again for females. And this is from Nordstrand, 2011. Okay, so there you have it. These are 2 practice articles, 2 quiz articles. Hopefully you're starting to get the hang of interpreting some tables and figures, presenting measures of association. Please post questions online for me, and I can answer any one of your questions.